Hello students, today we will discuss electrophilic aromatic substitution. So first of all, what is electrophilic aromatic substitution? Electrophilic aromatic substitution is defined as a reaction where an electrophile replaces a hydrogen atom on an aromatic ring and it requires a catalyst. In the process, a less stable carbocation intermediate is formed, and this carbocation intermediate it is known as sigma complex. Electrophile reacts with an aromatic ring. This is an aromatic ring. For example, this is benzene, and this electrophile it attacks on benzene, and the substituted product is formed. One hydrogen from here it is replaced as H plus, and electrophile comes in place of hydrogen. Electrophilic aromatic substitution, if we see here, so one hydrogen it is replaced, and electrophile it goes to the carbon like this, and we get the substitution product. So any electrophile can get attached to any carbon. All carbons in the benzene ring are here same. So this electrophile may be attached to the here. It can replace this hydrogen also. It can replace this hydrogen. Any one hydrogen can be replaced. So what is electrophile? Electrophile, it is electron loving species, and it is a positively polarized species. It is an electron poor species, means it requires electron, can form a bond with nucleophile. Electrophile can form a bond with nucleophile, and it can accept a pair of electrons from a nucleophile, and it may be neutral or positively charged. So electrophilic aromatic substitution, it occurs in 3 steps. So what are the 3 steps? The first step is the generation of electrophile. So first we have to generate an electrophile, and it requires, for generation of electrophile, it requires a catalyst and formation of carbocation intermediate. The second step is the formation of carbocation intermediate, and the third step is removal of proton from the carbocation intermediate. So these are the 3 steps in the electrophilic aromatic substitution. So these are the electrophile, the acids which are H plus donors, for example H3O, hydronium ion, alkyl halides and carbonyl compounds, alkyl halides and these carbonyl compounds. So these are the electrophiles which can serve as electrophile. If you say here, if an electrophile attacks on benzene, so benzene serves as a nucleophile. This is the benzene plane of the ring, and each carbon has unhybridized p orbital and contain 1 electron each, and these unhybridized p orbitals are the perpendicular to the plane of the benzene ring. So these are the delocalized electrons on above and below the plane of the ring, and they form the electron cloud like this. The concentration of negative charge above and below the plane of benzene ring carbon atom is the most important feature for an attacking reagent, electrophile. Electrophile can attack only on this negative charge, that is above and below the plane of the ring. So generation of electrophile, if we take an example, how we can generate electrophile, for example, in the halogenation reaction. If we take one example, if a compound have an electron deficient orbital, for example, aluminum chloride, FeBr3, the aluminum and iron, they have an electron deficient orbital, and a complex is formed with an electrophile. FeBr3 iron third bromide is a strong Lewis acid. Aluminum chloride is also a strong Lewis acid, and iron can accept electron pair. Similarly here aluminum, it can accept electron pairs. The central atom iron has empty d orbital to accommodate electron pair from the Lewis bases, for example bromine. And by this process, generation of more reactive electrophile occurs. This is the purpose of taking an Lewis acid. So we have to produce the more reactive electrophile or more powerful electrophile. For example, if we say here iron third, it has empty d orbital that can accommodate electrons from the bromine. So formation of electrophile, for example FeBr3, when it approaches to the bromine molecule, the electron pair, it goes to one of the bromine, and this gets positive charge and this gets the negative charge. And this complex, that is electrophilic complex, is formed. So FeBr3, it is a Lewis acid, it polarizes a Br-Br bond, and one bromine atom becomes highly positive. So this is an electrophile. So, and this is electrophilic complex. The electrophile reacts with the nucleophile benzene. Now we have electrophile and it reacts with the nucleophilic benzene ring. Benzene ring is an electron-rich species, and it gives a non-aromatic carbon carbocation intermediate, or this is also known as arenium ion, sigma complex, or Wieland intermediate. Because benzene is aromatic and carbocation, it is non-aromatic here, and this carbocation intermediate, it is known as arenium sigma complex or Wieland intermediate. The intermediate formed has not an aromatic structure. यहाँ पर जो है, it doesn't have an aromatic structure. It is an unstable cation with only 4 pi electron. Benzene has 6 pi electron. It is double allylic and it has 4 pi electron, that is delocalized over 5 carbon atoms. This positive charge delocalized over 5 carbon atoms. The sixth carbon is a saturated carbon atom, that is sp3 carbon. This is now sp3 carbon. These are all sp2 carbons and form a sp3 hybrid bond. Now it forms a sp3 hybrid bonds. Loss of a proton from the intermediate. Now this proton may be lost. Loss of a proton from the intermediate results in regeneration of aromatic ring. That is substitution product of benzene. Here we can see here, for example, when electrophile approaches to the benzene ring, these electrons move here and electrophile attached to here, and we get the resonance hybrid of these 3 resonating structures, and this is the resonance hybrid. Intermediate formed is less stable than benzene because it is non-aromatic. So the intermediate, that is carbocation, it is less stable than the benzene, and reaction of electrophile with benzene has high activation energy, and intermediate carbocation loses hydrogen ion and produces stable substitution product. This is the carbocation. This has high activation energy and it is less stable. The first step it is slow, and because this is unstable, the second step it is the fast, and we get the substitution product here. So this is the electrophilic aromatic substitution. The next lecture will be halogenation of benzene. So thank you very much. Please subscribe the channel Globe All Chemistry. So thank you once again. Thank you.